Good morning, everybody. I'm Glenn Heaston. I'm your moderator today. Welcome to the ASFPM annual conference, the virtual version. Much like last year, if you were attending that, we welcome you again. We thank you for your participation in this session. This is session A3. It's called 2D Floodways, the Confluence of Modeling and Regulations. I wanted to thank our sponsors as well. Without our sponsors, this conference could not be as awesome as it is. And so I encourage everybody to go to the virtual conference hall, or the virtual hall where our conference sponsors are located with their booths, and pay them a visit. I will remind everybody that these presentations are all pre-recorded, and so as such, any dialogue that happens will need to be through the chat. And I do encourage you to submit questions during the presentations. Submit early so that we can get them staged properly, and our presenters who are behind the scenes right now live can prepare for those questions. But we will have three sessions today, or three presentations today, and I will introduce each one as we move forward. The first session is called two-dimensional floodway testing and evaluation. And we have two presenters. The first presenter, the primary presenter, is Isaac Allen. And Isaac is a water resources engineer in the surface water department at AECOM. Over the last 5 years, he has been primarily involved in H&H modeling for floodplain development and mitigation projects, with a recent focus in developing 2D models for regulatory flood studies. Isaac received his Master's of Science in Water Resources Engineering from the University of Buffalo in Buffalo, New York, and a Bachelor's of Science in Environmental Engineering from Syracuse University in Syracuse, New York. We'll have about 3 minutes of time at the end of this presentation for questions. So again, please type in your questions as soon as you have them so that we can make sure we get to them as best we can. So with that, let's go ahead and roll the presentation.
Hi, and thanks for attending this presentation of the ASFPM virtual conference. My name is Isaac Allen, and I'm a water resources engineer with AECOM, a member of the Compass PTS. For this presentation, my colleague Andy Bonner and I will be talking about 2D floodway testing, a project that we've been working on with FEMA over the last year and a half. Before jumping into the details of the 2D floodway testing project, I wanted to spend a few minutes going over some of the key events that led up to the project. As many of you know, the use of 2D models, specifically via the HackRAS platform, have continued to gain popularity. And because of that, there's a number of regulatory challenges that need to be faced. In 2019, recognizing some of these challenges, FEMA created the 2D Floodway IPT group, or Integrated Project Team. The goal of that IPT was to look at updating guidance to address the regulatory compliance for 2D floodways specifically. The group met and established some of the key issues that needed to be addressed right away, and worked over the past couple years to update guidance. That updated guidance was released in December of 2020 and is available now for you to look at. As you might anticipate, when it comes to 2D modeling, there are a number of areas in guidance that will require some update to better represent the capabilities of new software. The same holds true with 2D floodways. After completing that initial round of guidance updates, there are a number of additional things that we'd like to investigate. A couple of those main questions that stood out were: one, what options are available to make 2D floodway generation more cost-effective, and what are the impacts of those? And two, can additional guidance be developed for making it easy to start and work through the 2D floodway creation process, and in addition to that, make 2D floodway creation more consistent, similar to the established procedures that are already available for 1D floodway generation. To address those questions, this 2D floodway testing program was put together. Through the program, we looked at a number of different tests to specifically look at how different components of the model and different techniques impacted the floodway widths and surcharges that were generated from the model. Unfortunately, due to time restrictions, we can't go over all of our testing results, but wanted to take this time to focus on some key areas that people would likely be interested in. The first of those tests that we looked at was how the new evaluation line approach that was rolled out in the updated guidance impacts floodway widths when you consider that approach versus looking at every element within the 2D floodway. More to come on that in just a second. The second thing that we looked at was hazard classifications and trying to identify initial encroachment settings based off of depth velocity hazard results. For that discussion, I'm going to kick it over to Andy later in the presentation. With all of these tests, we also kept in mind how the updated 2D floodways that we were putting together compared against the effective information, to keep in mind the transition between effective models, which were traditionally done with 1D HEC-RAS, and updated 2D models, and see how differences may have played out with that respect. These next couple slides overview the project areas that were selected for the floodway tests. When selecting our project areas, a couple things were kept in mind. One, picking areas where 2D models had already been created, thus allowing us to include the most number of project areas possible. And two, making sure we had good variability captured in our project area selections. That included both geographic variability across the different FEMA regions, variability in the stream characteristics that were represented, and also variability in the models that were used to generate the 2D floodways. The image on screen here shows the counties where streams were studied. As you can see, we had a good sampling across the country. Counties that are in red were part of our first round of testing, and counties that are shown in blue were part of our second round of testing. I'll go into a little more detail about the difference between the first and second round of testing later on in the presentation. This next slide here shows a table with some additional characteristics for each study area. As I mentioned, we tried to capture a range of different models as well as a range of different geometry setups in the models. You can see we had some study areas that used SRH2D as well as a number that used HEC-RAS. Of the ones that used HEC-RAS, we had some that were 2D detailed models, some that started as 2D BLE models but were refined to use in this program, and some that represented a 1D 2D hybrid setup. On the far right side of the table, you can see some basic characteristics of the different streams that were selected. As I mentioned at the beginning of the presentation, one of the areas we wanted to focus on for this presentation was results of our evaluation line versus all cells tests. Before going into any of the results, I wanted to take a second just to review differences between those two methods, the evaluation line method and the all cells method. The evaluation line method was first introduced in the guidance that was released at the end of last year, and the all cells method is also described in that guidance. To show the differences between the two approaches, I wanted to use a basic schematic. The image on the screen here represents a basic 2D model results, where you can see a number of different model cells, as well as the cells that are included within the 1% annual chance floodplain in blue. With the all cells approach, essentially what's happening is that your floodway surcharge is evaluated at each model element that's within your identified floodway area. As with the 1D floodway, you identify the location, the area that represents your encroachments. Those encroachments are then applied to your model, and the model is run with the base flood discharge. Once you have your results, you then compare the water elevations from that run to your original 1% run and see what your surcharge is at each element within the floodway. With that all cells approach, the same requirements that you would have for a cross-section apply to each cell. That is, that the surcharge at each cell must be less than 1 foot or the more restrictive state requirement. And any location that has surcharges less than 0 must show that there's no adverse condition created. For the evaluation line approach, the same basic setup is followed, with one major exception. Once the floodway run is completed with the encroachment set, you evaluate surcharge at each model element, but in addition to that, a number of evaluation lines are selected to perform surcharge averages. An evaluation line is most commonly a contoured BFE line that's selected to perform that average. In this schematic, the evaluation lines are shown in the pink segments. The difference with the evaluation line approach is that your surcharge requirements are now evaluated on these evaluation lines with some additional considerations for the cells not included in the surcharge averages. In order for a floodway to be compliant with this evaluation line approach, the average surcharge along each evaluation line must meet the 1 foot requirement or more restrictive state standard, similar to a cross-section. The additional criteria that were included for this are that any cells that contribute to that surcharge average must be within half a foot of the required surcharge range. And in addition to that, all other cells within the floodway must meet that same criteria of being within half a foot of your established surcharge range. In addition to that, any model elements that intersect an insurable structure must meet the 1 foot surcharge criteria or more restrictive state standard. Now let's jump over and look at some results from our evaluation lines versus all cells tests. For each area, a 2D floodway was constructed using the evaluation line technique as well as the all cells technique, and the results were compared together. One of the main outputs of those comparisons was a plot or figure similar to what you see on the screen here, where the evaluation line floodway is in pink, the all cells floodway is in blue, and the effective floodway is in black. We put together these plots to get a general sense of differences between the two approaches. Due to time restrictions, we can't go through all of these comparison figures, but what I've done is put together some of the highlights we are seeing from the different test cases available. The first takeaway from our set of results was that in areas that have flat topography with slow subcritical flow and largely 1D flow characteristics, there's minimal differences between the evaluation line and all cells approach. One such example is shown on the screen here. The key here is the plot in the upper left-hand corner, which shows the surcharges along the evaluation line that's pointed out with the arrow. The average surcharge along the evaluation line came out at about 0.73, and you can see that all of the cells that contributed to that evaluation line average only varied by about 1/10 of a foot across that entire segment. As a result, the floodway widths are very similar. Another takeaway from our evaluation line tests is that, again, similar to the last example, where 1D flow characteristics largely exist, and even in a 2D model, there are going to be almost no differences between the evaluation line and all cells approach. Where you do have some 2D flow characteristics, such as areas that have storage or attenuation into the overbanks, you may find minor differences between the evaluation line and all cells approach, but especially at the map scale, those differences likely are not going to be very significant for the floodway that's being generated. The final takeaway to highlight here is that across the different testing areas, the main potential we saw for differences between the all cells and evaluation line approaches was in areas with complicated 2D flow characteristics. In these situations, if evaluation lines aren't placed at a high enough density and major 2D flow paths are missed, you could see differences between the two techniques. Guidance on this is already included in the December 2020 update. However, to better understand these, we looked at some additional areas with complicated 2D flow characteristics to see if any additional refinements to the guidance would help to eliminate situations where this might occur. Once adding in those additional testing areas, we were able to confirm that as long as evaluation lines are placed sufficiently, major differences between the all cells and evaluation line technique can be eliminated even in areas with complicated flow characteristics. With that said, these additional areas have shed light on some additional opportunities for guidance and additional questions to answer related to 2D floodways. One major question that came up is surrounding floodway islands and the inclusion or exclusion of islands within the floodway. When using the depth velocity approach as your method for setting initial encroachments, you could identify some limited conveyance areas within the middle of your floodway. In these areas, a decision has to be made whether or not to include or exclude them. Largely, this will depend on a community's decision on how they'd like to manage the floodway, but presents an additional topic of conversation related to 2D floodways and whether or not specific guidance should be set on including or excluding these areas. An additional thing that came up is the procedure for evaluating surcharge averages where there are splits in the floodway. There are a couple different ways to approach this. One approach is to include a surcharge across all different branches of the split paths. That would result in one surcharge area across the multiple split flow segments. The second approach, which is shown on the bottom left of this slide, is to break up your average into essentially 3 independent evaluation lines. This approach is preferred because it does not allow the surcharge average on one of the reaches to influence another and therefore result in a narrower floodway than you should have. As a result, this type of information will be included in future guidance to help refine a situation like this. As with all things 2D floodway, there's likely more to come, but for now I'll leave it at that. And I want to turn it over to Andy Bonner to talk about some interesting results surrounding hazard classifications and initial encroachment settings for 2D floodways.
Great, thanks Isaac. So the next set of 2D floodway exploration and testing that we wanted to share with you is related to leveraging hazard data or depth and velocity data to help inform initial encroachment placement. The question we wanted to ask ourselves and try to answer was whether we could use that hazard data to help reduce the number of iterations necessary to land on a floodway delineation that would comply with regulatory surcharge limits. So in 2020, the guidance and standards were updated related to floodways. And one of the shifts or the adjustments in one of the standards was to replace the equal conveyance requirement with something a little broader that would comply or would at least apply to both 1D and 2D. So there was this reference to equitable consideration of both overbanks, hydraulically speaking at least. And the way to do that, outlined in the guidance, was to leverage the depth and velocity data from the 1% annual chance unencroached floodplain for that purpose. So as this slide reflects, the first step would be to leverage that depth times velocity data out of the 1% chance floodplain to select an initial depth times velocity value, a contour on either side of the stream center line, and then to place encroachments at that location, run the model, and then check it to see what the surcharges were and whether it's in compliance. And then to iterate on that until reaching a point at which the overall floodplain would be, or floodway would be in compliance. So 2D models simply take longer to run, especially if you're using unsteady flow. And therefore you can imagine how long and the time constraints that would be if we had to do 10 or 15 or sometimes even more iterations until those floodway surcharges were in compliance. So what we wanted to test, therefore, was if we took several 2D modeled streams that were available, delineated the floodways for them to meet surcharge requirements, and then compared those encroachments back to the underlying depth and velocity data of that 1% base floodplain to see if there would be any common linkages or trends. For example, if we went through all the different iterations in the procedures that I just mentioned and delineated the floodway for one of the streams at a depth times velocity value of 5, and that happened to be what it took to reach surcharge compliance for that location. Did that apply to just that one stream, or would it apply to all the streams? Or at the least, if we use the simplified categories outlined in the flood depth and analysis grids guidance that FEMA's produced, would compliant 2D floodways generally have their encroachments fall within the medium category or the high category or something else? Or separately, what if we use the flood hazard classification methodology that's been used in parts of Australia, represented by the chart on the bottom, where 6 different classifications are defined based on the specific depth and velocity at that location? Would compliant 2D floodways always fall in the H3 category or the H4 category or something else? Or were we simply just not going to be that lucky? Well, unfortunately, at least at first, we weren't that lucky. So kind of to pause and to rephrase the question we were trying to answer, was there a way to initially estimate where floodway encroachment should be placed by using depth and velocity data? Could we cut down on the number of iterations that it took to produce a compliant 2D floodway to arrive at a delineation that would meet those regulatory requirements? And so what we started to look at was, again, whether there was any correlation there. And if you can tell from this table that's shown on the screen, the third from right column, that is the value, the depth times velocity value that was used to place the encroachments for each of these different streams. And you can see those are all different values. And the second to last column and the last column on this just show what that associated range or that category was where those floodway encroachments were placed as it relates to the FEMA classification and the depth and analysis grids guidance and in the Australian classification. So it was clear that there was no one-size-fits-all solution based solely on a standard depth times velocity value that always seemed to work. It certainly varied by stream. So we next kind of asked, the next question we asked ourselves was whether that variation could be tied to other stream characteristics. Did larger streams or steeper streams or floodplains with wider or wider floodplains generally correspond to higher depth times velocity values, or would we see other trends begin to emerge? So in order to test this idea, we decided to look for correlations between the depth times velocity value, or that contour where the encroachments were placed, and the different floodplain characteristics such as average slope, average top width, drainage area, peak discharge. We also decided to look at this from the context of the mean or the average depth times velocity over the entire floodplain, and as well as the standard deviation. So we knew that we would be somewhat limited given the small number of streams available for testing at the time, and so our conclusions would likewise be limited, but our hope was that we'd at least start to see some trends that we could build on over time as more and more 2D floodways get completed. So these are the correlation plots for some of those floodplain characteristics that I mentioned previously. For those that are unfamiliar with these types of plots, the closer that the R-squared value is to 1, the better the correlation. Anything close to 0 is pretty poor. So in these cases, the y-axis represents the depth times velocity value at which the floodway encroachments were placed for each 2D model stream. And the x-axis represents the corresponding value of that particular stream or floodplain characteristic being tested. So as you can see, at least from this small sample size, there didn't appear to be any strong correlations between the depth times velocity and the drainage area or the stream slope or that floodplain top width. However, while not great, for sure, we did see at least a little bit more correlation between the selected depth times velocity value and the average depth times velocity across the entire floodplain. So viewed another way, we looked and performed a very simple regression analysis with all the previously mentioned caveats about limited number of test locations and so on, where we could plot the actual value of the selected depth times velocity value on the y-axis and the predicted depth times velocity value by that regression equation on the x-axis. Obviously, a perfect answer would be one where the actual value and the predicted value line up along that 45-degree line and match one another exactly. So anyways, without drawing too many definitive conclusions yet, there at least was enough here that spurred our interest to explore a little bit further. The mean value is one statistic only. There's others, but it encompasses a lot of individual detail into that one value. So that brought us to this stage. The three examples shown on screen were 2D modeled streams that were part of the test data set where we had floodways delineated. Each was somewhere around 5 to 7 miles in length and was at least in the ballpark of one another as it relates to the average depth times velocity value of their floodplain. But as you would expect, their flood characteristics were very different from one another. Some, like the top and bottom examples, had more variability in their depth times velocity values than others, like the one in the middle. Similarly, some had very lower depth times velocity values in the overbank, but very high depth times velocities in the channel. So another way to look at this is to use a histogram. So we did that, created a histogram of the total hazard or the total depth times velocity of the entire floodplain. And this was informative and that helped illustrate some of that variability in a floodplain's hazard or hazard distribution, depth times velocity data. So one of the great things and one of the nice things about depth and velocity data is that in what it reveals about the characteristics and uniqueness of a particular floodplain. So at least for the purposes of this exercise, it became less relevant to know what the drainage area or the stream slopes were, for example, because the depth and velocity information inherently would reveal much of that. Flatter streams, for example, would generally have lower velocities on average than steeper streams. Larger streams with larger flows would often have higher depths of flooding on average. So some of that DNA, per se, of the floodplain is manifested in its depth times velocity profile or visualization of that depth times velocity grid. So therefore, although we could have extracted several other statistics or unique information about the data, we were curious what would happen if we did this same simple regression analysis looking at both the mean depth times velocity and the standard deviation of that depth times velocity. So maybe unsurprisingly then, when we performed this simplified regression analysis with both that mean and standard deviation of the DV, we actually observed some pretty favorable results. In nearly all cases, the predicted depth times velocity by that regression equation was within a value of 2 plus or minus of that actual depth times velocity value that was actually selected to produce a compliant floodway with surcharge requirements. So one of the takeaways from this is that even if it's premature to publish an actual equation as guidance until more streams can be analyzed, at a minimum, there's optimism that we could provide a suggested starting depth times velocity value for a mapping partner to produce an initial floodway encroachment that would at least put us in the ballpark of something that would produce a surcharge-based floodway in compliance. And hopefully this could be at least a way to reduce the number of 2D floodway iterations that might be needed to land on a final delineation that both meets that equitable consideration standard and surcharge requirements in place. So I won't go into too much detail on this, but another area of exploration that we started to look at was to break out the total depth times velocity of the entire floodplain by its channel and floodplain only portions. And preliminary testing of that was pretty positive, actually. Could be another alternative for refining how we might estimate the starting depth times velocity to use for where to place initial encroachments when performing a 2D floodway. But in conclusion, one big takeaway, of course, is we just simply need more data points. More streams would be needed to fully confirm some of these initial findings and certainly to provide us with a level of confidence in publishing them as some sort of best practice.
And Glenn, will you
but there's at
be
least some
repeating
optimism here.
The questions
eventually, these results will be shared with in more detail with the 2D floodway IPT that FEMA formed a couple years ago, as we discuss if or how we might work towards future updates of guidance with some of these applied approaches and lessons learned. So with that, we appreciate your time and we'll open it up to questions. Thank you.
Thank you very much, Isaac and Andrew, for a great presentation. about the 2D floodways and regulatory issues. Certainly a very timely topic, as 2D floodways and 2D modeling in general is becoming quite a popular thing in the United States, around the country. It certainly is in the state of Illinois and some of the Midwest, although you guys weren't studying anything specifically in the Midwest, it didn't look like, but we do have a few questions that have come in, and we have about 3 minutes to answer them. So let me start with the first one from John Matthews. General question that he says applies to both presentation number 1, which we just saw, and the second one that we haven't seen yet. That in the past, FEMA has limited the modeling to steady state flows through reaches. And he says, I noticed that in these presentations, they're including unsteady flow. Is FEMA considering moving to unsteady flow as a basis for hydraulic modeling?
Yeah, I can take that. So first off, great question. Thanks for adding that in. So I'll note that in the most recent guidance update that came out in December 2020, it's not prescribed whether or not you need to use steady or unsteady. Both options are on the table. And I will also note that both options are described in that guidance as to how you would perform a floodway using either steady or unsteady. And then I'll also add in that that's an additional topic that we're looking at through this testing effort, and we'll continue to kind of look through and hopefully include some updated guidance and as we get more results and better understand the difference between the two of them.
All right, the second question is, how do you determine the initial depth times velocity value? And would you expect a consistent depth times velocity value for a particular geographic area, like a countywide study, or vary from watershed to watershed, even if whoa, things moved on me. Even as the watershed changes from geographic area?
Yeah, I'll take that one, and that's a great question, and one that I think we all ask ourselves to start from a lot of options and narrow down to something that's a little bit closer to what the final answer is. And the reality is, from again the small amount of testing we did, is that there isn't a consistency there. Even within the same geography, it could change. It's so dependent and unique to the characteristics of the stream. Again, how wide it is, how steep it is, and even within a same geography, often those change. And so what we found, and I think what we hope to continue to explore, is that looking at the depth and velocity that are unique to that floodplain, that particular floodplain where you're adding a floodway, that we can kind of use that information and come up with an initial depth times velocity. And the hope is that within future guidance updates, we'll be able to provide a little bit more around that hopefully will help mapping partners start from a better initial place.
Thank you very much. Well, we've run out of time for questions, but even though we still had a few on queue yet, so let me encourage folks who still have questions to reach out directly to our presenters today. There's information online through the FEMA guidance documents. I know that some people are looking for a link possibly to the FEMA guidance. So if we could, maybe the speakers could post a link into the comments that might help answer a few of these questions without doing so right now on the live call here. So we're going to transition again. Thank you very much, Isaac and Andrew, for your presentation. We're going to transition now into the next presentation, and this presentation is called 2D hydraulic modeling, including multiple levee systems and floodway analysis, a case study of the Payette River in Payette County, Idaho. And this is, I guess, an application of 2D modeling in the real world. Lori Schrader is the lead presenter. She will also have co-presenters, Erica Schmitz and Will Zung. Lori's bio reads, as a water resources engineer and a project manager for Stantec out of Overland Park, Kansas. While at Stantec, Lori has worked on a variety of hydrologic and hydraulic modeling projects through the US related to FEMA flood studies and levee analysis. She has her master's degree in civil engineering from Purdue University and a bachelor's in civil engineering from UCLA. I will remind our attendees, please post your questions during the presentation if you have any, so that they can get in the queue. This presentation is recorded, but we'll switch into the live Q&A at the end of the presentation. We'll have a little more time at the end of this presentation for questions, roughly 9 or 10 minutes. So with that, let me go ahead and have the video roll for the second presentation.
Hi, my name is Lori Schrader, and I'm a project engineer with Stantec. Today I'm going to be one of the presenters for our Payette River and Payette County, Idaho study. It's a 2D hydraulic model that involved multiple levee systems as well as floodway analysis. Joining me today is going to be Erica Schmitz, who is a project engineer, and we'll also have Will Zung available for questions. He is our levee subject matter expert. We like to start our meetings at Stantec with a safety moment. So just a quick spring cleaning reminder as we're cleaning up our houses to remember not to rush, be careful when moving larger heavy items and not to overexert yourself by carrying too many things, and always to remember to put away your cleaning supplies so that children and pets don't get into them. Today's presentation is broken up into 4 different sections. First, we'll give a brief introduction and background of the study area and why 2D modeling was chosen to model this river. Second, we'll go into the actual 2D model setup, some discussion about data availability and decision making to develop the HEC-RAS model. Third, we'll talk about actually applying the 2D results into the regulatory mapping products. And finally, we'll share some obstacles and things to consider when it comes to these complex 2D models. We'll share some lessons learned as well as try to answer some of the questions that came up along the way, like how do you capture different model extents when there's multiple scenarios that go into a single regulatory product, how to calculate and communicate values in the floodway data table from a 2D model, as well as making sure communities understand and are comfortable with the results from a 2D model. The study area for this project is the Payette River in Payette County, Idaho, which is located in western Idaho. The Payette River flows from east to west through the county until its confluence with the Snake River. It has a very large drainage area, and there are some upstream reservoirs, but about 80% of the drainage area is downstream of those reservoirs, so it is fairly unregulated. There are some USGS gauges along Payette River, including one that's in Payette County, and the most significant floods at that gauge were recorded in 1997, 1964, and 2010. The current effective mapping along the Payette River is from a study done in 1982. So since then, there have been some significant flood events along this river. The Payette River in Payette County, Idaho is a very complex hydraulic system. The river flows from east to west across the county and is defined by a very wide and shallow floodplain. The effective 100-year floodplain is shown on this image here, and in many locations it's about a mile wide. On top of that, the channel itself is a braided channel with multiple irrigation ditches, subchannels, and adjacent tributaries that join the floodplain. So a 1D model really wasn't going to accurately capture how complex this system is. On top of that, there are 6 non-accredited levee systems that line the Payette River in this county. And because the purpose of this modeling was to develop a regulatory detailed study, we were going to also do some floodway analysis along this stretch of river.
Hi, my name is Erica Schmitz. I'm a Water Resources EIT with Stantec. First, I'm going to go through the main modeling parameters used to develop this 2D model. HEC-RAS 5.0.7 was used for this model. Flow was introduced into the model at 3 different boundary conditions: an upstream inflow hydrograph for the Payette River and at 2 significant tributaries which confluence with the Payette River along the modeled reach. The 2D domain was extended up the tributaries so flow could be introduced upstream of the tributaries' confluence with the Payette River. All 3 hydrographs were temporally adjusted so the modeled flow at the downstream extent matched the gauge analysis peak discharge. For this model, a 1 meter resolution LiDAR DEM was used for the overbanks, and bathymetric survey data was applied to the channel where available. Manning's N values were developed based off of the National Land Cover dataset, and refinement regions were used to adjust this dataset along the stream channel and significant roadways. A 200 foot by 200 foot cell size was used to generate the 2D mesh, and the mesh was refined by placing break lines to capture hydraulically significant features and to define the stream channel. Orienting cell faces so that they were perpendicular to the flow helped reduce irregularly high velocities in the model. Significant structures were added to the model with connections in the 2D domain. Bridges cannot be directly modeled in the 2D mesh with HEC-RAS version 5.0.7. This capability has been added to HEC-RAS 6.0, but this model was developed before the beta version was released. Bridges that were overtopped were modeled as a connection with a culvert or a series of culverts. For bridges where regulatory events did not hit the low chord, a modified connection with no bridge deck was used, as seen in the slide. This method had the closest match to losses found in a 1D bridge under low flow conditions. As mentioned previously, there are 6 levee systems along the Payette River in Payette County. All 6 levee systems along the Payette River are non-accredited and do not currently meet the data requirements outlined in 44 CFR 6510. Following the FEMA levee guidance, both with levee and natural valley analysis were completed for the river. Natural valley analysis is used to determine the levee impacted area and assumes the levee does not impede flood flows, allowing conveyance landward of the levees. For the with levee analysis, all of the levee systems were represented in the 2D mesh with the connection, ensuring that high ground associated with the levee was captured along the 2D cell faces. 6 natural valley geometries were developed, 1 for each levee system, to analyze each levee independently of the others. This allowed us to determine the impact of each individual levee system had on the water surface elevations along the Payette River. For these scenarios, the connections were removed and the cells reoriented such that the cell faces were aligned on the riverward and landward sides of the levee, thus allowing flow to cross the high ground. 2D floodways are a fairly new concept. There are 3 main options we considered for developing a floodway in a 2D model. One option is to modify the terrain so that the flow is contained in the channel. Another option is to add lateral weirs to the geometry, which blocks flow from the encroached overbanks. The final option is to adjust the N values in the encroached overbank so that they do not convey any flow. Each method has several pros and cons for their use. The raised terrain method was used in this analysis because it did not require a modification to the geometry. A drawback of this method is that the terrain needed to be modified outside of HEC-RAS. However, HEC-RAS 6.0 has the ability to do this terrain modification in RASMapper. The raising N values method was not used in this analysis because that method allows for storage in the encroached overbanks. This resulted in extremely narrow floodway because so much storage was still available in the extremely wide encroached regions. The lateral weir method was mainly not used because it required a modification to the geometry. Another drawback was that HEC-RAS can be sensitive to long connections in a 2D mesh. Since the modeled length was 33 miles, there were multiple flow paths that needed along the river. Using connections as lateral weirs resulted in longer computation times and issues with the geometry. To apply the terrain modification, the encroached region of the terrain was raised so that the flow would not enter into the area. The floodway is defined as the portion of the floodplain that conveys the most floodwaters. In a 1D steady-state model, the encroachments are placed on either side of the channel so that equal conveyance is maintained. To accomplish this result in a 2D unsteady-state model, the initial encroachments were developed using a single depth velocity contour to account for equitable reduction in the flow from either side of the flood area, and they were limited to the main channel. This initial run was modified to get acceptable surcharge values by adjusting the depth velocity contour and by adding additional flow paths. For this model, there were over 30 separate floodway runs, making it a very time-consuming process when compared to a 1D steady-state floodway. In a 1D floodway, the surcharge is calculated at each cross-section and the allowable values range from 0 to 1 foot. In a 2D floodway, surcharge was calculated in 2 ways. The first is at each cell. If the cell overlaps an insurable structure, the allowable surcharge is 0 to 1 foot. For all other cells, the allowable surcharge is -0.5 foot to 1.5 feet. The second way surcharge was calculated was with a weighted average along a BFE line. The BFE lines, also referred to as evaluation lines, were used to report the floodway. BFE lines span the entire width of the floodplain and follow one water surface elevation value. The allowable surcharge along the BFE line is 0 to 1 feet, which is the same as a cross-section in a 1D model. The FEMA floodway guidance document provides a general method for calculating the average surcharge along the BFE line using the unit discharge. There are several different approaches that can be used to calculate the average surcharge. For this analysis, the depth velocity grid was used to calculate the weighted average because it comes directly from the model and it's related to the unit discharge. Once all the modeling was completed, our next challenge was to create the regulatory data. The challenge was to convey the same information provided with a 1D model, but with the 2D results. 1D and 2D both generate a similar SFHA, as seen in the side-by-side comparison, so there's not too many differences with those layers. In a 2D model, straight cross-sections are typically used to report modeled elevations. In contrast, base flood elevation contours are used in the 2D model. The BFE contours tend to make the maps look more busy, requiring more judgment to determine which contours should be mapped, attempting to capture the detail generated in the 2D analysis, but also keep the maps readable. In the 1D model, cross-sections are also used to report details of the floodway analysis. As discussed earlier, this data is captured in the 2D model through evaluation lines. Evaluation lines need to be selected so that they cross only one profile baseline, span the entire width of the floodplain, have a spacing which corresponds to the panel scale, and are relatively straight so that the reported values accurately represent the floodway analysis. Once they have been selected, the evaluation lines are then used to generate the data that makes up the floodway data table found in the flood insurance study report. Another large difference is that profiles are not required for 2D model data. To create the regulatory data for this model, first we need to determine which natural valley scenarios needed to be included. The scenarios are included if the levee is determined to be hydraulically significant. The FEMA guidance describes 3 scenarios which indicate if the levee reach is not hydraulically significant. The first scenario is that the levee is fully submerged and the landward conveyance is in the direction of river flow. This didn't really apply to any of the levee systems in this modeled reach. The next scenario is that the lateral exchange of flow across the levee that is overtopped is insignificant, or it does not exist because water level on the landward side of the levee equalizes with the flooding source. This also didn't really apply to our levee systems. The final scenario is when the height of the levee is low compared to the water surface elevation over the crest of the levee for the majority of the length of the levee. This also did not apply to any of the levee systems modeled in this reach. For this reach, the differences in inundation area between the width levee and natural valley results were negligible, but comparing the water surface elevation, these levees do provide some hazard reduction to the area landward, even though most levees do not tie into high ground, making every levee system in this reach hydraulically significant. This is the final combined SFHA. The hatched regions are areas where a natural valley analysis dictates the base flood elevation. The natural valley analysis allows for additional conveyance and/or storage of floodwaters in the landward side of the levee. These scenarios generally result in BFEs that are lower than the width levee analysis in the channel and higher than the width levee analysis landward of the levee. While the overall inundation extents are not significantly different, polygons were used to capture the extent of each natural valley scenario that was used to develop the final regulatory water surface elevations. The floodway data table is one of the most difficult components of the regulatory data to produce. The data that is reported in the floodway section of the floodway data table is taken directly from the model in a 1D floodway analysis. For the 2D floodway, these values had to be calculated outside of HECRAS. There's not a documented procedure for how to calculate these values in the FEMA guidance or technical references. The width was easily measured using the evaluation lines, and the section area was calculated using the evaluation lines terrain data and the floodway scenario water surface elevation grid. The depth velocity grid was used to calculate the mean velocity along the evaluation line with the same weighting procedure used to calculate the surcharge. In a 1D model, there is one possible elevation along the cross-section for each scenario. To report the 1% annual chance flood water surface elevation values, these are pulled directly from the model results. In this 2D model, the regulatory dataset is a combination of all 7 scenarios and has backwater applied from the confluence with the Snake River. This dataset was used to generate the evaluation lines. So the elevation along the evaluation line is consistent for the regulatory water surface elevation. Unlike in a 1D model, the water surface elevation for the without floodway and with floodway results can vary slightly across the evaluation line. For those scenarios, the water surface elevation grids were also averaged across the evaluation line. Finally, the increase, also known as the surcharge, was calculated with the weighted average discussed earlier.
Finally, we wanted to discuss just some general considerations when it comes to these complex 2D models. The first thing is the runtime. So a single simulation for the Payette River model took approximately 4 hours to run on a desktop computer. 2D models generally take a lot longer than a 1D model to run. Because the different recurrence intervals that needed to be studied and the 7 different scenarios with the non-accredited levee systems, it resulted in 42 different simulations that needed to be run. On top of that, the floodway analysis itself is a very iterative process and took upwards of 30 simulations before it was fully refined. Another thing to consider for these models is the actual data size itself. So a result file for one of these simulations was upwards of 1 gigabyte total. When we're looking at 40 plus different simulations, you can see that that model size is quickly going to become very large. One thing that we did to try to combat that was separating our with levee and our natural valley modeling, just so that the data could be packaged up and transferred a little bit easier, but it's still going to be very large model sizes. Finally, another thing to consider is the confidence that you have in your hydrologic input. We were very lucky that the Payette River model had a USGS gauge with a lot of historical storm data, so we were able to develop the input hydrograph based on gauge data that was actually recorded along this stream. But if that's not available, it's just going to add some additional uncertainty to the total volume of water that your 2D model is experiencing.
Another aspect to consider is there's currently not a layer in the DFRM database that is able to capture the model extents used to create regulatory products when multiple scenarios are used. We use polygons to designate the model source and extent for regulatory purposes, as well as documenting this in the report and the project narrative. A big thing to think about is documenting how all the values were calculated in the floodway data table. Each user might use these values in a slightly different way, and knowing how they are calculated can help the end user. For example, typically in a 1D floodway analysis, the difference between the without floodway and the with floodway is the increase. That can still be the case in the 2D floodway analysis. However, since all of these values are averaged separately, slight differences could also occur, and that could be totally acceptable.
Another challenge with these 2D models is how to communicate these results to the public who's going to be using this data. So while we have higher confidence in these 2D models with these complex systems, the results themselves are going to be looking a lot different than what would traditionally be on a flood insurance rate map developed using a 1D model. So outreach to communities is going to be very important to make sure that they understand what this data is and why it looks different than what traditionally might be on a flood insurance rate map. For the Payette River study, in conjunction with FEMA Region 10, we developed an online viewer so that communities could actually pan through and look at these results in their own time. Further down the line, when this project progresses, we'll actually meet in person and have more opportunities to go through the data and make sure that the community is comfortable not only with the modeling and the results, but how the actual mapping looks as well. Thank you for attending our presentation. Hopefully you found it interesting and learned something along the way. I'm Lori Schrader. You also heard from Erica Schmitz, and we have Will Zung available as well to answer any questions you might have.
Thank you, Lori and Erica, for your presentation. That was really interesting. I'm impressed with the project that you've done. Boy, combining levee analysis with floodways and 2D certainly has been a challenge, but I'm glad that to see how you were able to make that work. And I think we're going to continue to see more of this kind of modeling going on in other parts of the country. Again, being from the Midwest myself, we're kind of at an earlier stage of getting this kind of work under our belts, but learning from those who have been doing it is very helpful. I also will direct attendees to the questions that have been coming in. Thank you very much for submitting questions during the presentation that we can kind of stage and think through. One of the responses from the last presentation I have left up, which is a link to the FEMA guidance document, the FEMA website which has the guidance documents, so that you can download the 2D modeling information from that if you need it. There are a number of questions that have come in now. They're being upvoted. And so again, if you see a question that you want to rise to the top of the pile, you can upvote that and we'll get to that first. So with that, let me go to our first question. And this is from Will DeRosette. How do you select your standard grid cell size, and how sensitive were your results to the grid solution? And did altering the grid cell size affect the floodway encroachment results?
I can go ahead and take that one. We selected the standard grid cell size in the initial model setup. So once that was selected, we didn't add iterations into that floodway analysis. So the whole base model was set up. All of those natural valley scenarios were all done with that analysis. So we didn't really test different cell sizes with the floodway runs. However, that grid cell size was selected. We did a sensitivity analysis to see how big we could go or small. And it really came down to, we had such a shallow area, so we didn't need a super refined cell size. And we were able to use break lines with that to capture all of the hydraulically significant features. Hope that answers.
Yes, thank you. I see also that Will Zung is also in the chat if he's needed for any comments. The next question is from Straven. It says, was the terrain modified first for the main reach and then the split flow section were done together after determining the main channel cannot handle it?
Yeah, I can take that one as well. Yes, the very first scenario was with pretty tight depth velocity encroachment selections, and then was limited to the main channel. And then each iteration we tried to determine which of the split flow paths were significant. And then again, using the depth velocity grid to determine which of those flow paths we were testing. So it was a very iterative process. And like I said, there was over 30 iterations of that process. So it ended up being quite time consuming to do it. But that kind of more leans towards the complexity of this model. And I think if you had a model with a little less complications with those braided flow channels, you wouldn't need as many iterations.
Okay, we have about 4 minutes left in our questions and answers section. So let's continue moving on here to more questions. Jay Springer asks, in the braided channel, did you find flows that varied in relation to the extent of how braided it was? And did you use data to compare this to the more open sections to determine the overall flow regime?
So I can speak to that one. One of the benefits of 2D modeling is that the model is kind of going to tell us what the significant flow paths are, since it's really driven by the terrain that you're using. We know that the Payette River was a really complex system that had many canals and adjacent streams running alongside it. And for those larger events that we were analyzing, that floodplain spread to encompass all of them. So we didn't really look at the specific flow paths individually until it came to the actual floodway analysis. As Erica mentioned, we first wanted to analyze just the main channel of the Payette River to see if it could withstand those flood flows with staying within the surcharges. And you can see by some of our mapping, there's no way that that was possible. We had to add in multiple flow paths to make sure that those surcharge requirements were going to be within those limits, and make sure that that flood flow could pass through those multiple flow paths.
Very good. We've got about 2 more minutes of questions. And again, I'm just going to go for the ones that have the most thumbs up. So Luke Carlson asks, quick question on the hydrology and hydrograph. Were the peak flows modeled to approximate the steady state, or did you model a more natural hydrograph with a hydrograph that rose and fell and allowed attenuation by storage throughout the model?
So for the hydrology for the Payette study, we did use a more natural hydrograph. There is a USGS gauge along this portion of the Payette River, so we had pretty high confidence in what that hydrograph shape should be, and we were able to use actual real-time gauge data of a significant storm event to actually scale that peak hydrograph to the 1% flow that we were mimicking. So in this case, we had high confidence that the overall volume that the system was experiencing was pretty realistic because we had that gauge data to back it up.
Very good. You guys are getting a lot of questions. And by the way, we had a lot of people on this session too. I was told about 268 people attended the session, which is awesome. Thank you for your attendance. And a lot of kudos are coming in here as well that I'm seeing in the comments. Next question, and we've got about another minute to go. What was the total duration for this effort?
So the modeling itself, it took a while. So the 2D model setup with all the iterations and refinement that needed to go into it probably took a month or two. And then the floodway analysis itself, since it was a lot of trial and error, as Erica mentioned during the presentation, we explored the different options of even trying to put in a floodway, that we had high expectations that we would be able to run through this pretty quickly, and we're kind of surprised with how many questions we ended up with along the way. So I think from start to finish, from just the modeling standpoint, it probably took about 5 or 6 months.
Okay. Well, that is all the time we have for questions today. There are plenty that we did not get to, and I apologize. For those of you who would like more time with the speakers to ask more questions, you can find them on the email or on one of the other sessions. I'm not sure. We can do some live chatting, I think, through messaging on the platform potentially. But please reach out to them with more thoughts and questions if you have them. The next presentation, the third one, and it's the last one of this section, is called Floodway Assessment 1D versus 2D Modeling Perspectives. And this will be presented by Stephen Sands from Hazen and Sawyer, and a co-presenter is Martha Cardona. So Mr. Sands has over 35 years of experience, including positions in the consulting industry and as a municipal employee with the Lexington Fayette Urban County government, and managing the Charlotte, North Carolina stormwater program. Mr. Sands' expertise includes NPDES MS4 program implementation, watershed modeling, and capital improvement project design. Stephen Sands graduated with a civil engineering degree from the University of Kentucky, and he is a professional engineer and a certified floodplain manager. So with that, let's go ahead and play the video.
Thank you. My name's Stephen Sands. I work for Hazen and Sawyer in the Charlotte office, and presenting with me today is Martha Cardona. She's with Hazen and Sawyer in the Raleigh office. Our presentation today is the comparison of one-dimensional and two-dimensional models, but with very specific focus on how a floodway differs between those two modeling approaches. Our presentation includes 3 sections. overview of a floodplain and a floodway, which is pretty basic. I think everybody will understand and has heard the definition of a floodway. We'll present two modeling exercise results where we compare a one-dimensional and two-dimensional model for two FEMA stream reaches, and we'll end with conclusions and discussions of those modeling results. Floodway definition. The first three bullets are straight out of the CFR. The floodway is the channel of a river that must be reserved in order to discharge the base flood. And you can see here we highlight the words cumulatively increase the water surface elevation more than 1 foot. We're highlighting the word cumulatively because perhaps part of the floodway definition hasn't considered lost floodplain storage or the cumulative impacts of the flood fringe filling. The floodway limits must be set to the combined effects of past encroachment. So when you're setting a floodway, you should look at all of the cumulative past encroachments to make sure that the overall base flood increases is less than 1 foot. And this third bullet is really the clear definition, or the definition that I always go to, is the floodway is reserved for flow depths and velocities that are hazardous. Flood fringe is ponding water. A floodway is water that's moving relatively quickly with relatively high depths. The fourth bullet is a rumor. My friends have been telling me this for my entire life. A floodway is areas where the depth and velocity is greater than 1. I don't know if that rumor is correct. I think maybe my friends have been lying to me. We'll assess whether or not my friends have been lying to me and see how, really looking at a two-dimensional model, what types of flood flow depth and velocity we get when we're defining a floodway, and what is a reasonable depth and velocity product in defining a floodway. This slide here, it talks about, it's my confession. I hate doing one-dimensional floodway models. I hate them because they are counterintuitive. You start by using a method 4. You set a target of an encroachment that would give you a 1 foot increase. You then adjust your target to perhaps a 0.8 foot target, 0.6, and you're assessing the results each time. But many times when you set your 1 foot target, you get surcharge values that are much greater than 1 foot. The challenge here is when you start mixing some of your encroachment targets, your results are counterintuitive. You set a lower target, like a 0.4 foot target, and you get a much higher encroachment. And so they're counterintuitive. So many times you're going through iterative loops, guessing on what your target should be. Spent many weekends trying to figure out how to go straight to a result of defining a floodway by using this method. But when you step back away from that, you realize, well, defining a floodway may have a little bit of arbitrary nature in it because it's being so counterintuitive, at least in some cases for some stream reaches. This is a tangential issue or a study that Dave Kanan and Tim Troutman, I'll give them credit, from Mecklenburg County, did a study 15, 20 years ago about the cumulative impacts associated with lost floodplain storage. And they did a pilot watershed where they assessed if we allowed flood fringe filling up to a 1 foot surcharge for a one-dimensional model, what are the downstream impacts associated with that lost attenuation and lost storage? And they showed that it was a 2.3 foot increase just due to the hydrologic changes. A 0.5 foot surcharge provided about a 1 foot increase due to hydrologic changes, and a 1 foot surcharge provided a 0.2 foot increase due to hydrologic changes. So that gives it, so in addition to looking at the surcharge value at your project site, part of a floodway may need to include looking at the lost storage and the associated impacts associated with the lost storage. The first case study is in Georgia at the Atlanta metro area, and It's Bell Creek in Gwinnett County. The drainage area is 1.9 square miles. The stream slope is 0.005. That's a relatively small watershed when you're talking about FEMA studies. It's a headwater FEMA study. And Martha's case study, when she presents later, is further down, and I think her watershed is about 39 square miles. So it's further down in the watershed. And you'll see different dynamics or different results between floodways, between the two watersheds. Northwest of Atlanta in Sewanee Creek, Buford Highway, Bell Creek is the receiving tributary below Lake Llewellyn. So the original model that we developed was for a breach analysis and emergency action plan to map where the breach due to a Lake Llewellyn failure would occur. And we had the model set up and were able to readily compare with a FEMA model. FEMA one-dimensional model, great FEMA model. You can see here we have the FEMA model, HEC-RAS, with Lake Llewellyn modeled. So relatively, like I mentioned, a steep tributary, 0.005, steep relative to FEMA conditions, draining down to Buford Highway. Two-dimensional HEC-RAS, fairly straightforward grid pattern, merging geometry within the channel to the overbanks and using LiDAR data information in order to perform that geometric development. I love the RAS Mapper feature with the two-dimensional flow models in HEC-RAS. You can very quickly look at water surface elevations, velocities, and they include this depth times velocity rumor that we've been talking about. They have a depth times velocity hardwired into the results. Two-dimensional model has the ability to look at the various effects of velocity through a cross-section, or here we're picking profiles, cross-sectional profiles showing the velocity distributions at different locations within the stream. So more accurate representation of what the floodplain is doing in both directions. So now we start comparing the two-dimensional model with the one-dimensional model. And you can see here at FEMA cross-sections, we're about 1/10 of a foot different. And that's incredibly close when we're talking about a model calibration and comparison between the two models. So we're very happy about differences that we're getting between the two modeling approaches in water surface elevations. Similar, when we've compared channel velocities, we're getting very similar channel velocities. 4.3 compared to 3.9, 4.3 compared to 4.1. Here we're seeing a larger difference, and that was due to the channel distribution, the geometric distribution of the channel compared to the one-dimensional and two-dimensional. So we drill down and say, why does that occur? And it's really the different geometry that we had in the two models. Now we start testing that rumor, depth versus velocity. You can see on the left, and we'll drill down a little bit in more detail on the next slide. The left presentation is the depth versus velocity product if we didn't have any encroachment at all, just a normal floodplain. And you're seeing some greens, some yellows. The yellows are a depth versus velocity of 5. The greens are maybe depth versus velocity of 4 to 3. And then within the floodway, you can see the dark line of the floodway, the one-dimensional floodway. You're seeing depth versus velocity up in the 10s. Much different, much larger than the depth versus velocity that my friends have been telling me of 1. When we encroach and revise the two-dimensional model, all or just about all of our depth versus velocities are up close to 10 within the floodway. So, our first conclusion with this is, wow, maybe our depth versus velocity definition of 1 is way underestimating the floodway impacts. Here we're drilling down a little bit more, just showing in more detail. And you see on the right, we're showing a depth versus velocity. Just about a good portion of the floodway along the entire reach has a depth versus velocity of a value of 10. So we start an iterative process and testing. Well, what would happen if we defined a floodway or tried to define a floodway based on a depth versus velocity of 1. And you can see here that floodway in red is much wider than the one-dimensional floodway model. So we test other model or other target values, a depth versus velocity of 5. And we're starting to see it getting closer to being coincident with the floodway width of the one-dimensional model. And we get to a depth versus velocity of 7. And that's pretty close to the width of the floodway. So a depth versus velocity is what we're seeing relative to a one-dimensional model. So that's a velocity of 3 feet per second and a depth of 2.5. That's what we're seeing within a one-dimensional model. And that, to me, is much larger than the depth versus velocity of 1 and some pretty substantial and hazardous conditions. Another test that we can look at is how did the channel velocities change? You can see on the left, we're showing channel velocity without the encroachments, and on the right, after we encroach to the one-dimensional flood model, we're seeing velocities increase all the way up to 5 feet per second within the channel. And similar story with stream power. So I'll turn it over to Martha. Martha will touch on a similar modeling approach, but it's a different watershed. It's in Raleigh and a larger watershed.
Our study focused on Crabtree Creek in Raleigh, North Carolina. It's actually a pretty large drainage area by the time Crabtree Creek gets to the corner of Glenwood and Creedmoor Road. It's about 100 square miles, so 93 square miles, not 39 feet, 93 square miles.
Sorry.
And it has a stream slope of approximately 0.1%. So it's a very large watershed, very different from Bell Creek. And so what we wanted to do was to compare a one-dimensional model as defined by HEC-RAS, using HEC-RAS, and it's a FEMA model. And we compare that to a two-dimensional model of the small ridge that you're seeing right there. So it's, it's just not a whole view of the entire creek, but just a ridge of within. And here we can see how the one-dimensional model is defined. It goes through the creek with its cross sections. It has information on different land uses, ranging from forest to parks to commercial areas and parking lots. So we wanted to study the extent and the nature of the different floods. We looked at the 10-year storm with the 1D model and the 25-year storm with the 1D model. And we saw that the 10-year storm really wouldn't impact any of the roads, Glenwood or Creedmoor, or any of the parking lots in the commercial area right there. The 25-year storm, on the other hand, would already show some of the parking lots being impacted and some flooding on Creedmoor Road. Then we wanted to compare, okay, let's look at the 1D model versus the two-dimensional model. We use the same topography as the 1D model. We use the same line views. We made sure that the same buildings that the 1D model wanted to capture were captured within the 2D model. Here we see that a 10-year storm, which is defined in a red line, has similar extents on both models. No impacts to parking lots or roads. The black line is a 25-year storm. And while the 1D model defined it with small impacts to parking lots, the 2D model actually found that there were more impacts to the parking lots and actually one impacting the Creedmoor Road right here. both models, 1D and the 2D, actually had similar extents for the 100-year storm, and both models predicted similar impacts to all parking lots in the area and to the roads, Glenwood and Creedmoor. So this has been really a very contentious stretch of the stream. It's always on the news when there are large storms occurring, and so as we will see in a minute. Here is a glimpse of the floodway within the 1D designated floodway, and here it is with the 1D model. We can see that it has surcharges that range from 0.6 to about a foot. If we would use that area of the floodway and put it in our 1D model to encroach the floodplain, what we obtain, just like in Lake Luella, basically, it was that we have much larger surcharges. They all went up by about a foot and over a foot, which is not really what we would want. So it leaves us thinking, okay, so what's really happening within this reach? Where are the high velocities occurring? How is the 1D model really depicting the hydraulics of it? Is it really capturing the entire picture? So we set out to look at the depths and the velocities of the creek as defined by the 2D model. And here I have highlighted some depths that occurred in various places away from the 1D floodplain. We can see that the depths overall range from 0 all the way to 15 feet, but some of these depths are actually even more than 4 feet, and they are not within the floodplain. And then when we looked at this color picture of the velocities, we see that the yellows, the reds, and the oranges are where the high velocities of approximately, from 3 to 5 feet per second are occurring, and some of those high velocities are away from the floodplain. So the 1D floodplain, the 1D floodway is not really capturing what is happening as high velocities and more dangerous areas. We know that those high velocities are very likely the result of all the obstructions to the floodplain that have happened within the years for all the development within the floodplain. And so what's going on is the water tries to rush through these buildings, trying to pass the 1% flood and creating areas that become actually hazardous. We know that, as I said, this stream has been pretty contentious. And so when there are high floods, there's always a problem here. And about 4 years ago, the USGS reported that approximately 7,600 CFS happened or got passed through the creek, causing great inundation. This is approximately an event that would occur once every 25 to 50 years, according to the distribution of flows from FEMA. And so the local news reported that Glenwood and Creedmoor was closed. There was flooding on Creedmoor, and then they had to close the street and evacuate some of the buildings. And then people posted pictures on the web and videos and basically showed, impacted areas. Here is the picture of a building that is really close to the creek, and we will see more detail on this, and very close to the creek, and already the flooding is coming up to the building. So let's look at what happened during that day. We can see here, we are right there, close to that building, and then we see how the stream came up to the building. The car is already within that inundated area. But when we look at what's going on, we see actually we can get a sense of the water moving quite fast, getting a view of really, indeed, it confirms, the model findings of this area got flooded. There are high velocities occurring in this particular area. So, how do we define a floodway in a more integral way, other than, our old definitions? So we, looking at the depth versus velocity, just like Steve was saying, we went and looked at depth versus velocity of 7, which is the purple area right here that I'm trying to point out to you. And we took that outline and said, okay, this is our new floodway. Let's look at what happens in the 2D model. And we observed actually there are pretty high surcharges when we encroach the 2D model with such a floodway. So D times V equals 7 is perhaps not necessarily, a straight good rule to go and model the floodway. How about if we try a lesser number? So we tried a D times V of 2, which is the red area right here. Very similar actually to the D times V of 7. We got lesser surcharges, but they're still above 1. So it's not necessarily what we would want. Why is it that we're not really getting, what we want if we pretty much define that area? So we said, well, let's just look at these colors in detail. We see that, we have the very pink and yellow and oranges are the enhanced areas of depth and velocity occurring in this reach, meandering all through these buildings where, the 1% storm is rushing through. We know that the D times V, perhaps of a lesser storm, potentially could capture, that floodway that we need. We see here that, the 10-year storm is really not capturing all of that area at all. It's leaving most of that area outside. And when we compare that to what it used to be, the 1D designated floodway, well, we see obviously it was, similar to the 10-year storm, leaves all that area outside. And it still, doesn't give us a good sense of the floodway. If we looked at the 25-year extent, this area is actually a little bit bigger than the D times V of 7 or D times V of 2. And indeed, it includes some of the parking lots that the D times V7 or 2 did not include. So it gives us some storage that potentially maybe, it could be that this is a good candidate to define the floodway. We don't know. We try that and see whether we would get better encroachment, better surcharges. We simplified the 25-year storm outline, tried it as a floodway, including, this area right there, the parking lot, and we saw that, yes, indeed, surcharges went below the 1 foot. So this basically gives us a glimpse of D times V concept. It's a good concept where we can start to, get a sense of what is needed to convey the flood, to convey the 1% storm, the enhanced areas of D and V that it's really needed to get that storm pass through. But then iteratively looking at potentially lesser storms could be what we need. So I will stop right there and turn it over to Steve.
Yes. So the conclusions. First conclusion is my friends have been telling me a D times V of 1 is appropriate. They've been lying to me, or at least what I'm seeing is that some of my friends have been lying to me. Maybe values of 5 to 7 are more appropriate, but that's probably only for typical floodplains like the Bell Creek floodplain, and more atypical floodplains that we're seeing like Crabtree Creek. You really have to drill down a little bit more into what the depths and velocities are. But Martha makes a good point here, is she starts looking at storm events. And it's interesting that a 25-year storm event is giving surcharges that are less than the target. So maybe the solutions are combinations of D times V and or storm events for different types of watersheds. With that, that concludes our presentation. Thank you very much.
Thank you, Stephen. Thank you, Martha. Really interesting presentation. I enjoyed it. It's interesting the times we live in with the data that's available and the tools that we have at our fingertips now. I'm reminded of the quote that you've probably all heard before from George Box that says, all models are wrong, but some are useful. So I think we can apply that here. It's interesting to see the difference between the 1D and the 2D components of studies. We have a lot of questions, and we only have about 3 minutes to get through them. So we won't be able to hit all of them, but I want to thank everybody for being so interactive with these sessions. We've been having quite a bit of attendance in this particular session, about 270 people. Let's go to Bill Brown's question. It has the most upvotes. It says, dynamic models account for impacts on lost flood storage and flood flow, resulting in wider floodway than one produced by steady state models. Have you compared dynamic to steady state models? Which model best reflects the impacts of encroachment that meet the FEMA standards and flood risk?
I can take that one. The straight answer is no. The study that you may be asking the question about is the Mecklenburg County City of Charlotte study, where they just checked impacts of lost flood attenuation, and that was done with a steady state model and was not done with a dynamic model. Would be much easier to do with a dynamic model. You could do it automatically, but that was not done.
Okay. Alan Uloff asks, is it possible that the depth times velocity equals 1 concept is based upon a zero surcharge floodway, or basically a natural floodway without surcharge?
I'll offer that. It's something that I've grown up with, and I don't know the origins. We presented at a state conference, and part of the first step of that state conference was to ask the audience how many had heard that depth times velocity as 1 defines the floodway. And about a half of the audience heard that. So we started in our presentation calling that a rumor, but your point in your question is maybe the depth versus velocity is more of a natural floodplain. And I've just been hearing incorrectly for quite some time, but it's grown.
Okay, we have one more question that I can get to, I think. And this is from Jay Springer. It says, do you notice that any pronounced erosion effects with the increase in velocity? I've always wondered if allowed development may impact downstream more with bed load than we have ever considered. Do you find anything like that?
Well, we didn't study that specifically with these 2 projects. Generally, you do see much increased erosion throughout the watershed. Part of that may be due to the encroachment due to lost floodplain storage, but probably the majority of that is due to the land use changes and changes in impervious.
Okay, well, we've reached the end of our session, and I'm sorry we can't get to the rest of the questions that are here. There's some very good ones. I will remind people that each of these presentations will eventually be reposted to be watched on demand. Also, the presenters themselves can be contacted directly through the emails that they have listed in their bios. The abstract page lists the abstracts and the speaker bios, so please check that out for any additional information to contact these speakers. I'll also tell you we have until 11 o'clock until the plenary session starts. So I would encourage all of you to do what you need to do to get ready for that 11 o'clock session and come back for that. Make sure that you visit our virtual exhibit hall as well and see our sponsors. It's really cool what this virtual hall can do. There's some really interesting exhibits there that will maybe surprise you with some of the creativity and information that's accessible, and being able to talk directly with people. It's pretty cool. So thank you for your attendance today. It's been wonderful. I hope you enjoy the rest of the conference, and we will see you back at 11 o'clock. Thank you very much.